All right, cool. Hi, my name is Abi Akar, and I also work at CSCS. And I work on a project called Arbor, and this is actually taken from our project. It's a multi-threaded tasking system. And we based our implementation, and this presentation is also based on a talk by Sean Parent. Yep, cool. And it's from his series called Better Code, and it's on concurrency, if you're interested to check it out. Okay, so a little bit of an outline. I'm going to be covering how to build a task system that runs on a thread pool. And I'm going to go through the design and implementation using a single queue method, and then building on that to use multiple queues instead. Then I'm going to compare the performance between single and multiple queues and a third library that already implements that. Then I'm going to talk a bit about exceptions and how to handle them in this tasking system and how to use them to get an early exit. And if you have any questions at any point, please stop me and ask. Okay, so as I mentioned, we implemented this for our library. So we looked at our application and tried to think of how we want to build this tasking system. So we have many tasks, and they can be of different sizes, and they can execute completely independently of one another, which means they can execute concurrently and in parallel. And so this is what we want to be able to support, to be able to execute these tasks. And our requirements are that we want to utilize our machine fully. Obviously, we don't want to spend a lot of time doing useless work, or worse, being idle. Well, not worse, just being idle. Also, we want to handle exceptions correctly, like I mentioned, and exit early if we have an exception. We don't want to execute tasks if we know that one of them already does something wrong. And also, we don't want to use any external libraries, and we want to keep the code short and simple because we have to maintain it at the end of the day. So we decided to build a tasking system, which consists of a task queue or multiple queues running on a thread pool. Okay, so here are some examples about how we ultimately want to be able to use this tasking system. So I have a couple of vectors, v0 of size n initialized to -1, and we have v1 size n by m also initialized to -1. And it's a very simple vector. I just want to set v0 and v1 to I and I plus j, respectively. Okay, cool. Yeah. So I want to be able to build the tasking system, TS in this case, and I want to be able to have some parallel function, parallel for, that takes this tasking system and takes the size or the extent of our vector, and just does v0 of I equals I in a lambda. And I want the tasking system to go and create n different tasks and set each element of v0 separately. I want to be able to do something maybe a little bit more complex, which is I want to be able to spawn a parallel for from inside a parallel for, which is what we're doing here. In the first lambda, which is my first task, I want to take a reference to v1 of I, and then I want to create another parallel for and set w of j as I plus j. So I want to be able to spawn tasks within a task in our task system. Okay, so there are existing libraries that do this. For example, Intel TBB, HPX, we've got also parallel patterns library, libdispatch, a lot. A lot of them are open source. They all support many platforms, and just feel free to use any of these. Our talk here is just kind of a reference implementation. We have our own reasons against using some of these. We did used to support TBB, but it became a little bit of a burden to maintain it, and we don't really want to force our users to install an extra library to be able to use ours. Okay, so now that we have the intro out of the way, we can actually look at how to design and implement the system. Okay, first of all, a bit of a recap about some of the data structures that I'm going to be using in this talk. I'm not going to be including using namespace std, and I'm not going to be decorating all of my data structures and functions with the std : just to keep things simple and the code uncluttered. I'm going to be using vectors and decs and standard functions and standard exception pointers. We already covered some of these things. If any of these concepts is new or unclear, feel free to stop me again. I'm going to go a little bit into detail about condition variables, just because I don't think they've been covered already, and we use them quite a bit. So condition variables are synchronization primitives, and they are used to block a thread or multiple threads until some shared variable is modified, and then the condition variable is notified. And I'll describe a little bit what that means. So a thread can kind of exist in two states. Either a thread wants to modify a shared variable, or it wants to wait until a shared variable has been modified. If it wants to modify a shared variable between other threads, it needs to acquire the mutex, and then access the mutex, do whatever it wants, and then it needs to release the mutex and notify all of the other threads that something has changed in that variable, so that the other threads can go and check it out. If the thread wants to wait on a condition variable, it needs to, again, acquire the lock and wait until it is notified by another thread that had accessed the shared variable. And when the condition variable is notified, then this thread will wake up and it will acquire the lock again, and we will continue execution. This is a little bit high level. We'll look at how this is actually used in the implementation. Okay, so let's look at the design. What we want is to have a queue of tasks that will eventually run on a number of threads, right? So we will call this queue our notification queue, and we will call the threads our thread pool, and we want each thread to pick up one of these tasks, execute it, and go on. And our task system will basically deal with the notification queue and thread pool. It should wrap it up. This is how we want the interaction to look between our task system and our notification queue and our thread pool. We want to basically just interact with our task system by running async. By the way, the solid line means data transfer, direction of data transfer, and the gray line is just like to tell it to do, it's a control, it's direction of control. So we want to be able to send our task system a task, and we expect the task system to just execute it. And we don't really want to care about anything else at this point from the user side. What the task system should do is it should push this task onto the notification queue, and then it should tell, the thread pool, okay, you can start running tasks. And then the thread pool should start popping tasks out of the queue and executing them until the task system tells the notification queue to quit, in which case we kind of stop executing. Okay, so our notification queue is essentially a blocking concurrent queue. We'll look again, maybe in detail, at what that means. Does anyone know what that means? Okay, so it basically means that our threads will kind of be blocked until there's something in the notification queue to execute. That's the blocking part. They will wait until there's something in the queue. And concurrent means it can be accessed by multiple threads at the same time. And our thread pool is just a vector of standard threads. Okay, so this is how we're going to implement it. I'm going to start with describing the task system class, and then go and describe the notification queue. So our task system basically contains a vector of threads. That's our thread pool. And it contains our notification queue, which we will see in more detail after we describe task system. When we construct our task system, we need to also create our threads. So this is where we do it. We create n threads minus 1 new threads, and we tell them to run this task loop. This run tasks loop is one of the methods of task system, and we will look at it in just in a few slides. When we destruct our task system, we want to tell the queues to quit, basically, to stop giving out tasks to execute, and we want to join our threads similarly to how we saw we handle standard threads in the previous presentation. Okay, so this is the run tasks loop that is executed by the threads that we created in the constructor of task system. It is an infinite loop, so while true. And what we want to do is we want every thread to always be executing tasks, right? So it will call queue.pop, which will return either a task from the queue, or it will return an empty task, and it should only return an empty task if we've called quit on the queue. So there are no more tasks to execute. And if the task is not true here, we're supposed to break out of our infinite loop because we don't have any more tasks to execute and the threads have done all of their job. Otherwise, our task has a task in it, has a function in it, and we want to execute our task. Okay, and then we have our async. So that's the user side function. The user at this point will give the system a task, and the task will just push it, the task system will push it into our queue. Actually, it will move it in to avoid an unnecessary copy. Okay? Okay, now to take a closer look at our notification queue, because previously we just looked, okay, we push to it here, and we pop from it earlier. So how are these pop and push functions implemented, methods implemented? First of all, we've been using the word task before. I should have mentioned this earlier, but it's just basically a function, a standard function. And now we're going to be using also lock, which is a unique lock of mutex, which was also mentioned previously in the previous presentation threads. Okay. So our notification queue has a deck of tasks. Deck is a double-ended queue. Yep. And this will be basically the thing that holds all of our tasks. It has a mutex because we need to control access to our shared variable, which is the deck. And it has a condition variable like we saw before. And we have a Boolean quit that tells us whether we are still trying to execute tasks from the queue or whether we've finished execution. Okay, so we have two main functions in our notification queue, a pop and a push. And this is how pop is implemented. The first thing we want to do is we want to lock our mutex because we want to access our shared variable, the deck. And then what we want to do is we want to, if there are tasks in the queue, we want to get a task and execute it. But if there are no tasks, then we want to wait until there are tasks. And this is what happens here. The condition variable calls the wait method, and it waits on this queue lock. And what happens at this point, if we enter here, we're in the wait, the thread is blocked. So the thread is doing nothing. It's just waiting until some other thread tells it, OK, now you can wake up. So the thread is just blocked here and sleeping. We can also be in this while loop if, never mind. OK, so if when we exit this while loop, so when the thread is woken up, it'll check, first of all, did I wake up because we've quit execution or because there are new tasks in my queue? If there are new tasks in the queue, we will come in here and we will move the top task from our queue, and we will pop the front of our queue, and then we will return task. If, however, we had called quit, then we will just return an empty task. So like I said before, this pop function will always return a task if there are tasks in the queue, if we are still in running mode, and it will return an empty task if we have quit execution. As for the push, what we want to do is, again, we want to access the deck. So we have to lock our mutex. And then we want to push back the task into our queue. We have the scope here will guarantee that when we exit the scope, the lock will be released. And then what we want to do is we want to notify the rest of our threads that we've added a new task to the queue, so that the tasks that are waiting here can wake up and, okay, now I've got a task, so I can go and pop the front of the queue. So this is what this notify all function does on the condition variable.
Sorry.
Yep.
Can you repeat again what exactly is notify doing?
Okay, so like I said before in the pop, we've got this wait method, right? So if one of the threads wants to go to the queue and get a task, but the queue is empty, then it will go into this wait function, right? And this wait function will block the thread, the calling thread. So the thread will just be sleeping. And it will stay asleep, it will stay blocked until some other thread calls notify, okay? Once another thread calls notify, this thread wakes up and it checks whether the queue tasks is empty and does the rest, okay? By the way, I didn't mention this, but the thread can wake up spuriously as well, so it can wake up even if it wasn't notified, and that's why we have a while loop around, because if it wakes up when it wasn't notified by another thread, it should go back to sleep until it is notified.
Sorry,
Yeah.
You mentioned at some point in the pop function, you return an empty task if
Yes. Here, so let's say we enter this while loop because we are not, the queue task is empty and we are still running. We could exit. Actually, let me go ahead first and explain the quit function. So the quit function will again lock the queue, lock the mutex, sorry, because it wants to modify quit here. And then it will notify all that it has modified quit. So if a thread is blocked here waiting on queue lock, it can also be woken up by the quit function, right? So if it is woken up by the quit function, then it will check that the queue task is empty or not. It will be empty because we've quit, or if it's not empty, then it will execute everything until it's empty, but then it's quit. But anyway, it will jump over this function at some point and return task. And if we jump over this branch here, then task will be uninitialized and it will just be an empty task. Does that make sense? No, it's okay. So basically, we can, okay, so this while loop, it has two conditions, right, on the while loop. It's that queue task is empty and it's not quit. So this while loop will break when quit is true, right? So if quit is true and queue tasks is not empty, so if we've finished executing all of the tasks in our queue, but also quit is true, then what we're going to do is we're going to jump over this branch and return task without initializing it here. So this will be an empty task, okay? But we will only have an empty task if we finished executing all of our tasks in the queue and we have called quit on the queue, okay? So that's the only condition we should be getting an empty task. Okay, is this clear so far? Because that's basically the implementation of a task system with a single queue. It's really simple. Well, it's short and simple. Once you really think about it, it takes a few minutes. But let's look at how this will behave in practice. So what we have here is we've got a mutex for pushing into the queue, and we've got a mutex for popping out of the queue. And you might think, okay, this is necessary. We can't really get rid of the mutex because we want to guarantee safe access to the stack. And there's no way around it. And sure, with this design, there's no way around it. But it does actually add a very big serialization overhead, this mutex synchronization. To see that more clearly, let's look at a case where we have a bunch of really small tasks that have already been pushed into our queue, and now we want to start executing them. So first, our first thread gets the mutex, starts executing a task, great, releases the mutex, which is automatically acquired by the last thread. But then by the time the last thread starts executing it, because it's such a short task, the first thread has already done with the execution. So the mutex moves around, but if you can notice, the execution of the tasks is not actually happening in parallel. We're actually, at the end of the day, kind of serializing the execution of these tasks. And this is because of the single mutex on the single queue that we are accessing. So if we measure performance of this for small tasks, we will actually get really bad performance. So we can move on to a better implementation with more than just one task queue. And it can look something like this. So now we give each thread its own queue, right? So in theory, the mutex will kind of always be free unless we're kind of pushing something into the queue, but there will be much less synchronization. Of course, now we need an extra layer of scheduling at the top because we want to make sure that each queue on average gets the same number of tasks. And then this should make things much better, right? But let's assume, again, that this first thread finishes all of its tasks while these other threads still have tasks to run on. Then what will happen is that this thread will just sit there idle and not do any work, which is, again, not great. So what we actually want is another layer of scheduling here where this thread can go and steal a task from another queue if for some reason its queue is empty or busy or something. So we want multiple queues running on the thread pool, and we want some layers of scheduling to make sure we push tasks evenly across the queues, and we want to be able to steal tasks from other threads' queues. We're going to be using the same structures as before, a notification queue. Now there's just multiple of them. And we're still going to be running on a thread pool, and the task system will still encompass the same things. We're just going to need to modify how these structures work. Sorry. OK, so now we're going to interact with our notification queues and thread pools just a little bit more differently. We're still going to be using exactly the same function to talk to the task system. We're going to be sending in tasks that we assume are going to be executed. And the task system will still have the push option, and the thread pool will still have the pop option from before. They're unchanged. But the thing to note about these push and pop functions, they're very forceful. They always return a task for the pop, and they always push a task for the push, right? So there's no way. You have to do it. But what we're going to add are these try push and try pop methods, which kind of optimistically assume that on the first try we try to push or pop a task, it will work, and we'll have succeeded in our efforts. And yeah, the quit and the run tasks stay the same. So let's start now from the notification queue and see how we need to implement these try pop and try push methods before we see how they're useful. OK, so for the try pop, the first thing that's different is that we're no longer forcefully locking the queue, the mutex. We are just trying to lock it. So what this will do is it will check if the mutex is free. If it is free, it will lock it. Otherwise, it won't lock it. It will return that the queue lock is actually false. So if queue lock is false, when we go into this if, we will skip it and we'll just return an empty task. Okay? And empty task means that we failed to pop a task here. Okay, but if we were able to successfully lock the mutex, we will check whether our queue is empty. If the queue is not empty, then we will get our task, move it out and pop the front, and we will return this task. If, on the other hand, we did manage to lock the mutex, but the queue is actually empty, then we're just going to return an empty task again. So this is all like just try once to do the thing. If you succeed, great. Otherwise, just return that you failed. And that's really cool because we never actually wait on anything here. We don't have the wait call for the condition variable as from before, and the mutex is even just trying to lock the mutex. We're not waiting for it. The try push is similar. So again, we try to lock the mutex. If we are unable to lock it, we just return false. We were unable to push the task. Otherwise, we push it back, and again, we have to notify our queues that we push something because we still have our original pop and push methods. And we return true because, yes, we were able to push back our task. Yeah. Is there a microphone? Okay.
So now queue task is a queue per queue, right?
Yes, so this is the notification queue, but now we have multiple of them.
So why do you still need the mutex?
Because we still need to pop and push to this queue, so we still need to guarantee access there. But also we're going to see we can steal from other queues, so we need to make sure that no two threads are accessing the queue at the same time. Okay, is everything clear so far? Cool. Okay, now let's see how we can modify our task system to use the new features of our notification queue. So, like I mentioned, now we have a vector of notification queues. Instead of just one, we have multiple. And we're going to add a couple of new things here. We've got the count, which just keeps track of the total number of threads. And in this case, it's also equal to the total number of queues because we have one queue per thread. And we're going to keep an atomic unsigned here index, and that's going to keep track of all of our tasks in the entire system. And we'll see why that's needed in a while, and it's initialized to 0. And we're going to modify all of our functions from before, and we're going to add a new function to be used in a little bit. We'll check that out. Okay, so let's look at how our constructor is different. Nothing really serious. We just need to initialize our count, and we need to create multiple queues now instead of just one. And our run tasks loop now takes an index, which is the index of the thread in the thread pool, and also the index of the queue in the vector of queues. And when we destruct our task system, we want to call quit on all of our queues now because we have multiple, and again, we need to join all of our threads. Okay, now this is the run tasks loop that is executed by each thread in our thread pool. And how is it different? So now let me explain the idea. What we want to do is we want to start from our own queue, and we want to try to execute a task from our own queue. If for some reason we are unable to get a task from our queue, we want to check our other queues. If we check our own queue and all of the other queues once and still are not able to optimistically get a new task, then we want to go back to our forceful pop, which is guaranteed to give us back a task. And this is exactly what we do. We start from our own index here, and we try to pop a task. If we actually get a task, that means great, we can break this for loop, and then we just execute it and try again. If we are unable to get it from our own task, we go through the rest of our queues. Once we get one, great, we just break out of the for loop, execute it. If we've gone through all of the queues once, and we still haven't managed to get a task, we will call this pop, which will go back and wait until there is some task in our own notification queue. Once there is something, it will return that task. Does that make sense? So the hope is that we never have to go in here, actually. The hope is that we will always manage to get something from try-pop. Of course, we have to just make sure that if that fails, we will get something correct in the end, and that's why we call our pop. As for async, this needs to take care also of scheduling, so putting tasks in the correct queue, right? And we do this in a simple way. We just keep track of our index, and we try to push the task into one of the notification queues going round robin. And we start from the correct one, so from the notification queue we would like to push a task on. We try it. If we are unable to succeed pushing a task onto that queue, we will try all of the other queues. If we still cannot push on any of the other queues, then we will go back to our forceful push and make sure we push it in the queue we wanted.
Basically, you distributed the task.
Yes. Yes, exactly. It's very simple. We just go, every task, we put it on one, then the second, then the third, and blah, and we turn around. And that's how it works. Okay, now I'm gonna introduce one more function, the try run task. And this task will just start from queue number 0, and it will try to pop a function. If it is able to try to pop a function, it will execute it and break out. Otherwise, it will try the rest of the queues and try again to pop. But it's not guaranteed to actually execute any function. And we'll see why we need this in a bit. So this is just, you call it from a thread. The thread is just trying to participate and do some good work. It tries to pop a task. If it is able to, then great, it's helping with the task system. Otherwise, what can we do? Okay, so that actually concludes the implementation of the task system with multiple queues. And we'll see how that performs in a little bit. But before we go on to that, I want to talk a little bit about an extra class called task groups. So far, we've only been communicating with the task system through an async function, right? Which just pushes tasks onto the queues and we know that they're gonna be executed at some point, but we don't know when they're gonna be executed. But that's not good enough, because at some point, we would like to know when the tasks have been executed. So very frequently, we'll have like a group of tasks that we want to be done, but then we want some sort of barrier to tell us when they've been executed before we can launch another group of tasks, right? And this is basically what we would like to have, right? We would like some wait function around this task system. And we can do that by adding an extra layer, basically, which is called a task group. And it's very simple. We will just have a counter that we increment every time we push a task from the task group. And then every time we execute one of these tasks, we want to decrement that counter. And so we know when the counter is 0 that we've executed all of our tasks in our task group. And then the wait will give us, yeah, okay, all of your tasks have been executed. So if you're waiting on them, now you can push in your next group of tasks, for example. Is that clear why we would want to use this thing? Sure.
So basically, it's like controlling the input of a user, what you're doing there, right?
Not really. So the user will still push tasks into the task system.
At any time?
Yeah, but, well, you have to kind of modify the way that you talk with this task system. So you collect a group of tasks, you push them all into the task system. Once they're all pushed, you can wait on them. It's an extra thing. You can wait on the group of tasks to be fully executed. Sure, Sam?
Just for a bit of context, this is used in our parallel for implementation so that we can do a parallel for And after we've exited the parallel for, we know that all the tasks that we're required to do in parallel are in fact done.
Yeah. So before, with our async and task system, we couldn't do that because we wouldn't know when the tasks have been executed unless we destruct the task system. But even when you destruct the task system, you don't really know for sure when they've been executed. Yeah.
With this method, you do not have a false positive?
What do you mean a false positive? Like it will return
You achieve 0, but the group task is not empty.
No, you won't. We'll look at the implementation. Yeah, so you won't be pushing tasks after you've, once you call wait, you know that you've pushed all of the tasks in, basically. And this is how we want to interact with our task system. So our task system now includes everything, the notification queue, everything we did previously. And we've got the async function from before, and we've got this try run task that I mentioned at the end. And we're going to be talking to our task group through run, which is kind of like async. Maybe a better name would have been async, and wait. So this is what our task group looks like. We've got an atomic of size t, and that's our in-flight. So this will control the number of tasks that are currently being executed in our task group. And we also have a pointer to the task system because that's where we're going to be running our tasks. OK, so when we construct our task group, we just store the pointer to the task system. We give it a task system. And when we destruct the task group, let's say we want to wait until all of the tasks in the current group have been executed. So how is wait actually implemented? While in flight is not 0, basically, we want to try run task. So this is where the try run task from before comes in. So in our thread pool, we have this master thread. And this master thread is basically helping with the execution because we wanted to do a busy wait, basically. So while it's waiting for in-flight to be 0, we wanted to participate in the execution of the tasks. And that's why we provide this try run task function. It basically allows the thread, while it's waiting for all the tasks to execute, to participate in executing the tasks. Does that make sense? When in flight is 0, that means we've finished executing all of our tasks and we can return. Now, as for the run function, it's basically going to call async, right? First of all, of course, it needs to increment in flight because now we have an extra task in our task group. And then it wants to push that task into the task system, right? But it can't just push the task, which is here f. It can't just push it as it is. It needs to actually send a reference to in-flight with it, because we want to make sure that as soon as the function f, the task f, is executed, in-flight is automatically decremented right after. Okay? And the only way to know when f is executed is through the task system, right? So we want to wrap the task f and in-flight together and send both of that into the task system. And we want the task system to decrement in-flight when it executes f. Does that make sense? So this is why we need this make wrapped function. And this is where the universal reference comes in. Can you see? We've got type name f, and we've got f ampersand ampersand. And this is why we use standard forward here. This is basically to guarantee that we copy the f or move it as we desirable. So if we have an r value, we want to move f. If we have an l value, we want to copy it. And this standard forward kind of guarantees that. Okay? That's basically all it is. Okay, so this make wrapped function actually makes a new class for us, which is this wrap class, which contains the task f, the function f. Now it's a template. And it also contains a reference to the counter, which is the in-flight, the number of tasks in our task group that are currently being executed. And we create this wrap function using this make wrapped function from just the slide before. And again, it takes f ampersand ampersand, so a universal reference, and it takes the reference to our counter, and it forwards it to the wrap along with C. Okay? Again, to move when necessary and copy when necessary. Okay, you might notice this callable f here, which is standard decay of f type. I'm not going to go into too much detail into the standard decay stuff. Maybe they'll be covered later. It just makes sure, basically, the idea is to make sure that we get the correct type of f to copy it into wrap, right? So if we have an int reference f here, standard decay will give us back an int. So it will remove references when needed, and just to make sure that we have the correct type of f. That's all I'm going to say about it. Okay. And our wrap function, again, standard forward to make sure we don't copy if we don't need to. We also should create our copy and move constructors, which I haven't put in here, because again, we never want to copy when we don't need to, because this is all happening in the back end. We want this to be as fast as possible. So if we can avoid a copy, we're going to do it. But this function right here is the main thing we actually care about. This is our calling operator. So when we send this wrap into our task system, and the task system pops it out, this is what it's going to be calling. And it will be doing the thing that we want, which is the actual task. It's going to be calling the task and executing it. And immediately after, it's going to be decrementing our counter. So this whole class, essentially, is to make sure that when we execute our function, we decrement our counter. Does that make sense? Any questions? Okay. All right, so that's basically what we have in our library. And this is the performance, okay? So on the vertical axis, I have the efficiency. And the efficiency is basically the ratio of time spent doing useful things over execution time. So we want this to be as close to possible, as close to 1 as possible, right? Because we don't want to be wasting time doing anything that's not really useful. And on the horizontal axis, I've got the task size per task, and it's in microseconds. Okay, so I've compared TBB, our implementation of a task system with multiple queues, and our implementation with a single queue. And as we can see, for small task sizes, TBB is quite good. It's better than our multiple queue implementation, much better than the single queue implementation. But what we don't really care about this range, because what we care about is what I've highlighted in green here. In our library, this is basically the size of tasks that we have on average. And in this range, we actually do really good, much better than a single queue implementation, and even better than TBB. So we're doing very well for our current application. There are further things we can do to our task system to make things faster, more efficient, but then we would be re-implementing TBB, basically. So we just have this small library that does what we need for now, and that's the win. Okay, sure, yeah?
How does it compare to OpenMP in performance or implementation?
We didn't compare to OpenMP, so we could use OpenMP in our implementation, but it's a little bit annoying in our library to do that. It would require changing some things, like we would have to we'd have to use OpenMP in the calling code as well, and so we never actually implemented OpenMP. But I guess it's good. It's not too bad. Okay. All right, so that was basically the tasking system. But now we have to think a little bit about exceptions, because any of these tasks can raise an exception, right? Something could go wrong. And we want to propagate our exception to the calling function. So if somebody tries to create a bad cell or something, we want to tell it, okay, you created a bad cell. So we have to deal with that. Because so far, we've actually fulfilled 4 out of 6 of our requirements. We're utilizing our machine well. we don't use any external libraries. Our code is really like a few hundred lines of code, so very simple. But now we have to think about exceptions. So, like I said, any one of our tasks can raise an exception. And when an exception is faced, we don't want to execute the rest of our tasks. We want to stop and return whatever exception we have. Of course, multiple tasks can raise exceptions. In that case, we don't really care which exception we return. We just return one of them. And I did say that we want to stop the execution as soon as possible. But we don't really care if we execute a few extra tasks before we stop the execution, right? So if we encounter an exception, but the other threads still execute a couple of extra tasks, maybe overwrite our exception, that's fine with us. And the reason I'm mentioning that is because when we relax the constraints on when we stop executing, we have some extra leeway in the synchronization constraints. We can relax our synchronization constraints. We'll see that in a bit. And the last thing I want to mention is that we want to do all of this, all of our exception handling stuff, in the task group. We don't want to include the task system in this, right? And this is because we want to keep things modular, and we just want our exception handling basically to be done in the task group, keep things separated. It's a nice feature to have. So we're only going to be modifying our task group. And the way we're going to be doing this is we're going to be adding this exception state member. And this is a class that I will define in a bit, but it's easy enough to understand how it works before looking at the implementation. And to do exception handling in the task group, we are going to modify the run and the wait functions. Let's see how. So the wait function, this is how it was before. Before we were just spinning on in flight until it's 0. Now, after in flight is 0, we want to check our exception status. And this function reset here, at the same time, reads the exception status and resets it to 0 or null or whatever, okay? So we get the exception status, and if it is true, so if it is set to something, then we are going to rethrow our exception, okay? So after we're done waiting, if we have an exception, throw it. Yeah, sure.
X is locked to the if, right? But you withdraw it. So like, I'm going to see something.
Yeah, so yeah, I'm going to be talking about, so this X is actually an exception pointer, and it manages exceptions. It basically manages exceptions, and it allows them to be moved between threads and to be rethrown using this rethrow exception.
Outside of this scope, then?
No, it doesn't. But when you rethrow the exception, I think it's, I don't know if it's copied or moved or something. It's just, it unravels the stack and it's rethrown anyway, I think. I'm not entirely sure about the details there. But it doesn't like need to live outside the scope. Okay. So we have our run function. From before, our wrapped function, we added in-flight to it previously. Now we're going to add our exception status to it as well. So we want to pass our exception status to our task system. So this is our wrap class from before. Now it has a reference to an exception status again. We copy it in, and then we need to modify our calling operator. So our calling operator previously was just executing calling f here. Now we want to put it in a try-catch block. But before we go and try to execute the function, what we're going to do is we're going to check the exception status. And if the exception status is true, then we don't want to execute the function. We just want to decrement the counter, okay? And this way, our wait will always, our wait will always go down to 0, but it won't necessarily mean that all of the tasks have been executed, which is fine because we don't want the tasks to be executed in case we have an exception.
You discard it, but then it continues working.
Yeah, we discard it, but it doesn't continue working. It just keeps going through the tasks and decrementing the counter until it is 0. So it's not doing work. It's not really executing the tasks. Okay? Okay, so now the final thing I think that we need to look at is our exception state. And this is what it looks like. We've got an atomic Boolean, which is this error thing, and it's initialized to false. This will just tell us whether we have already encountered an exception or not. And it's got the exception pointer, which, like I said, just manages exceptions, basically, and it allows them to be moved between threads and rethrown again. Okay? Sure. So an atomic is like a thread-safe type. I don't know how to explain it, but it makes sure that it makes sure that you modify it all in one step. Can somebody help with the explanation?
Yeah, so atomic operations happens by ensuring that that operation cannot occur at the same time by multiple threads. So if you have multiple threads executing atomic, they will be serialized one after the other.
Yeah.
How the hardware implements it is basically you basically lock the bus, you do your stuff, you do your operation, and you block the other threads. This is the basic way in which you can implement atomic. Now, there might be more sophisticated way of doing it, but
It's like if you had a mutex in your variable?
yeah, only that you don't pay the price for the mutex. The mutex is a very heavy object, so you have also waiting tasks, you have queues of tasks that have to be, that you have to awake, something like this. This one is really an atomic operation. It takes just the time to do that instruction. So whenever you can, you should use atomics and not.
Yeah. It's basically to avoid having a race condition without having mutexes, I think. Yeah. Okay, cool. Thanks, Maura. So we want to implement a couple of functions on our exception state. The first one is this bool thing, which checks whether it's true or not, essentially. And what we want to do is we want to just load the error, which is our atomic Boolean. And we want to do it with the memory order relaxed. Now, this is a little bit more tricky, why we can get away with this. I can talk about it in the end if we have time or if you're interested. It's just related to relaxing our synchronization constraints, which I mentioned before. So this allows us to execute a few extra maybe tasks even after an exception has been caught, and it won't make anything wrong. But it's a little bit tricky to explain. I can go over it in the end if necessary. Okay, our second function for the exception state is the set. So after we find an exception, we want to save our exception pointer. And we also want to store true in our error here. And then we want to lock the mutex because we're modifying our shared variable, the exception, and we want to move our exception pointer. Reset, I mentioned before, what it does is it clears the exception state and returns the previous exception pointer that was inside. So we move the exception pointer out, we store false in our Boolean, and we null out our exception pointer, and then we return our old exception pointer. Okay. So basically with that, we have implemented all of our requirements, and that, I think, concludes my talk. Yes? Thanks.
So I think there is a little problem though with the exception handling.
Okay.
So this design doesn't provide basic exception guarantee.
Which is, yeah.
Which is, so it basically means that if exception happens, there is no way to correctly restore the state, because we don't know exactly where, so what functions are executed and what not.
Yes,
And
I think that's
this makes, so, and this is fundamental. It makes kind of useless to use exceptions, because, well, you only so exception handling mechanism is quite is quite expensive, and it makes sense to use exceptions if you have the ways to recover from your from the error, and only in that case. And but in that design, it's not clear what you're going to do after. You got an exception. How? So for example, if functions so usually meaningful exceptions are related to input-output, yes? And for example, if functions do output, what to do?
Okay, so the way we use exceptions is basically to print out error codes for the users right now. So we don't actually we don't actually handle the exceptions in any meaningful way. We don't try to return back to our state or anything.
Yeah.
Yeah.
That's basically, so in this case, the alternative is to just print out the error message in place in the thread that does where the error occur.
But yeah, Sam wants to say something. Yeah.
In the context of this tasking library, we're using it within, in fact, a library that's offering simulation services to user-side code. And we don't know much about the execution environment of that user-side code. It could be in the case where output cannot be seen or output is not even connected to anything. And throwing an exception, even if we can't do much with it, is a way of indicating failure in a way that can be handled appropriately by the user-side code that we don't have control over. The tasks that can throw will be throwing, again, because of a problem in the user-supplied functionality. Any other sort of exception is actually a bug in our code. So even though the user code cannot recover the state of the simulation after an exception is thrown, they will be able to handle the error case in a way that's suitable to whatever their context is, which we can't know.
Yeah, that's basically it. Sure.
Could you please comment again on why the single queue system is so bad for small tasks?
For small tasks, yeah. Because we will be spending most of the time waiting on a mutex. So imagine you have this queue with small tasks, and you have a bunch of threads that want to execute tasks from the queue, right? And to get a task from the queue, they need to grab a mutex, right? And they're all forcefully just waiting for that mutex. Once one of them gets a mutex, great. It will get the task, release the mutex, and start executing the task, right? And then another thread is free to grab that mutex, Correct? Okay, great. But by the time this mutex exchange is happening and the thread popping is happening, the task may have already executed, right? So in the end, you're spending more time waiting for the mutex, more time waiting to get the task than actually executing the task. So you end up in the end kind of serializing the execution of tasks just because you're spending so much time waiting on mutexes. And that's basically the reason why it's quite bad.
So does that mean with your plot that locking takes about of the order of millisecond, or at least several microseconds? So if I understand you correctly, you're saying it's problematic to have only one queue as soon as your tasks are actually quicker.
It's not that. It's just basically my idea of all of that is that we don't want to be competing to get that mutex. We don't want to be spinning on a mutex, because once you're actually spinning on a lock, you're not doing real work. You're just waiting for a lock. And I'm not comparing the time of the task to the time of the mutex, although probably of acquiring a mutex, although probably we could look at that. But it's just more about the idea of we don't want to spin on a mutex. We don't want to do work to get the task. We want to do the work to execute the task, right? And as much time as we can shave off trying to acquire the task, that's good, right? Because we just want to spend all of our time doing useful work. Okay, and yeah, when we have small tasks, basically the time to acquire the mutex becomes much more significant than when we have a large task. With large tasks, where you acquire mutex much less because it's a large task, and also, yeah, and so you don't really see the overhead of waiting to acquire that mutex. And Sam has a comment as well.
The other problem is that the contention on the mutex increases with the number of threads. So even for a fixed size, if we want to go on a larger multi-core system, then we get less efficient if we have to compete. But if we have multiple threads, then we can reduce that problem significantly.
Yeah, that's a really good point. Because we run on systems with like 256 threads or something, and then you've got 256 threads and one mutex, and they're just going to all be waiting for that mutex at some point. Yeah. Cool.
I have a question about why is TDD faster for small tasks? Is it because of word stealing or because of mining?
I don't actually know everything. I know they do a lot, that sounds expression, yeah. They do a lot to make things faster. And there are some things that we didn't explore. Like we could try to push or pop several times over the queues, like spin over the queues several times instead of once. There are a bunch of micro optimizations that we can use to make things faster. Yeah.
But that TBB uses word stealing, and it's done in a intelligent way, in a sense that when they split the work, they create a work tree, and they steal always from the rightmost tree, something like. So that they are trying to do in smart ways, because it comes from Silk, and Silk was developed by the same guy that developed FFTW, actually. So, by the way.
I didn't know that. Yeah.
Yeah, and then Intel basically gave him money and bought the thing. But yeah, that's very, very nice stuff.
One last question. In which countries are you using this task management system?
We use it to do things like create our cells, right, and do things to our cells. So our library, we have networks of cells. We can have up to millions of cells or something. And so we use our parallel 4 to create our cells, do things to our cells. Can't remember all of the things, all of the reasons. I think that's mainly it. We do it to parallelize the work that on ourselves.
I think, and this is, I think, a good example in which you really are separating the scientific side from the implementation side, right? So. She has the requirements for what she has to do, but she's not the one writing the scientific codes. She's just giving the.
And our users
abilities.
actually never call this task group or task system directly. They call a function that calls this under the hood, so they don't have to deal with any of this. Yeah. Yes?
Just on that point, this is where the exceptions become a problem. The phase of creating the cells in our simulation calls back to user-supplied codes via a so-called recipe. And we can't really control what they do in that class. It's really executed in the user side, and it may throw. And that's what we have to handle.
Yeah.
But have you measured the overhead of having exceptions instead of simply doing the catch and print out the error and let the thing fails somehow?
I don't have numbers on that, actually.
I was about to say they don't have the numbers, but we do know that it does take a long time if we've got a large number of cells. The process of building a cell from a user description can be very expensive. And if there are, again, thousands or millions of cells and they're all broken, then we're doing 1 million broken instantiations can take a very long time.
Oh, okay. Yeah.
I see. Okay. Yeah. If one is broken, probably also all the others are broken. That I see. Makes sense. All right.
Yes.
Good. Thank you. Yep.
Sure.
Just in one of the last slides, you have like the implementation of an operator. I'm not clear what Boolean. I think the one before.
This one?
Ah, yeah.
Yeah?
I just don't quite get that. I mean, like, is the parenthesis operator you're implementing?
Yeah. So this is the Boolean. Here, right here. When it reads the exception status, this calls the Boolean. It just checks whether it's true or not. Okay? So when you do...
So that parenthesis that is there...
Not exception status calls the Boolean here. This is it, right? It returns a bool whether it's true or false, basically. It treats this whole struct as a Boolean. So when you... Whoops. So basically, what are you doing here? You're treating exception status as Boolean, right? Either true or false. So what is this Boolean? It's this thing. This is what is called. Does that make sense?
Whenever you have an if, whatever is in parentheses, you need that to be a Boolean, right?
Yeah, it's kind of like, it's changing that struct into a true or false. And this is implemented using this bool function.
Okay.
It's kind of like any of the calling operator or something. You're not calling .bool, you're just calling it, and it calls bool.
If I understand that, like, you call the parenthesis, and then whatever you put in that parenthesis, it returns Boolean, which is true or false.
No, this again, it is a conversion operator. It's operator bool, which means...
It's kind of like the brackets in a vector or something, right? You're not calling dot operator brackets. It just knows to call the brackets underneath.
I didn't know you could overload like bool, because it's what do you call a type, right? Like.
Yeah. So it's
a type conversion thing. It's really explicitly defining how you convert exception state class into a Boolean.
It's like when you overload an addition or a subtraction or something. It's an operator, okay?
And you can do it with any type, operator type. Yeah, we did it yesterday with int. There was an example with int, and now you could do it with basically all the types.
It's a good practice to do that operator explicit.
Okay, yeah, it's possible. It's possible that I forgot to add it, I mean.
Yes, if you put it explicit, as the example we had, you had to do static cast bool. No.
In that usage, it will work.
Oh, in that case, it will work, and you don't have to cast it? Okay. It doesn't seem to be explicit. It doesn't speak. Okay.
Yes, this is how it's implemented for function, attendee function, for example.
Right. It's done that way.
Okay.
Yeah, cool. Other questions? So apparently we have to go to visit the machine room now for some reasons. So we can just step out and go to the visit.
Okay, great.